Time has come to actually talk about BGP. Now, I may have mentioned a couple of times during this training that I consider BGP not really to be a routing protocol. I consider it to be more of a policy implementation protocol. Now, what I mean by that is that BGP can be used, of course, to route traffic, but it really is a way for us to implement some of the business decisions, some of the non-technical decisions, some of the non-technical policies into our network so that we can deliver the traffic where we want it and how we want to deliver this traffic. And for this reason, BGP can from time to time be intimidating and overwhelming in its use of multiple attributes that it has available to it. And it's not as simple as other protocols on a matter of simple metric. For example, OSPF simply looks at the cost of the route and the lower cost wins. With BGP, metric is important, but we have things like the weight, the local preference, the origin, the actual metric or the multi-exit discriminator as it's called in BGP. So we have all these different things in BGP that can be used to determine which path is the best. And the reason why we have so many options in BGP is that sometimes our business decisions are not as simple. So sometimes we want to send the traffic to one of our ISPs and not to other ISP just because we don't actually like that other ISP, or that business decisions or even sometimes political reasons prevent us from actually sending traffic down that path. So the complexity in BGP comes actually from the need to implement all these business decisions, all these perhaps non-technical decisions into a routing protocol. So having a simple protocol that makes determination just based on one parameter may not be enough for everyone on the internet. So that said, the primary purpose of BGP, so when we talk about BGP, the primary purpose of BGP is to interconnect different autonomous systems. Now, what are autonomous systems? Now, there are many different definitions about the autonomous system, but one that I like the most, it's a network or a group of networks under the same administrative control. And a common routing policy. And you gotta love theoretical world, because this sometimes is not actually true, especially the common routing policy and when you're dealing with really large autonomous systems. But I digress there. So the autonomous system is a network that has the same administrative control. That means it may be managed by same team or group of teams, group of people, and that they are implementing the same common routing policy. Now, what I mean by the common routing policy is that when you have an autonomous system on the internet, no matter how complicated it actually is, no matter how many routers it has, when we look at it from the BGP perspective, actually what we are seeing is just a very simple dot on the internet that might be connecting to another similar dot. So we don't actually care what are the complexities of this autonomous system. We don't care how complicated it is. All we care about is that if they say they can deliver traffic somewhere, they can deliver the traffic. So all the internal complexities of this autonomous system are actually hidden from us. So a tool that is used to interconnect these autonomous systems is BGP, the protocol that basically holds the internet together, the glue that holds the internet together. That's the primary purpose of BGP. It is designed to interconnect these different autonomous systems. Now, when we have that primary purpose of BGP in our mind, what we have to keep in mind is another purpose of BGP. So let's say that we have a relatively large network that may consist of multiple routers. Now, in this network, sorry, we may have connection with some other similar autonomous system here. And between these networks, we are running the BGP. Now, all these networks here, all these autonomous systems, they may be running some internal routing protocol. And there may be many such autonomous systems on the internet. And the number of these external routes that might be exchanged in BGP is really large. And IGPs are not actually designed to carry a large number of routes. They're designed to carry maybe a couple of hundred routes, maybe a couple of thousand routes, but sometimes with some routing protocols, when you reach to 15, 20,000 routes, they may begin to struggle with these many routes. But BGP is designed to carry a large number of routes. Actually, at the moment we are doing this, our BGP routing table, I believe, has somewhere around 475,000, maybe even more, thousand routes. So this is the full BGP routing table. We are talking about a really large number of routes. Now, the secondary purpose of BGP is to actually remove the strain from internal protocols from having to carry this large number of routes. So not only that we are going to be talking BGP between the autonomous systems, but we actually need to sometimes talk BGP inside the autonomous systems to actually communicate these routes across our autonomous system. So inside autonomous system to carry the external routes. Or as in BGP terminology, which is technically speaking the ISP terminology, we usually call these customer routes. Even though necessarily they're not always customer routes, we might have the P routes, the transit routes, but any external routes that are outside our autonomous system, the good common practice in production networks is to actually carry these routes in BGP and not actually redistribute or touch your internal routes for this. Now, for this purpose, BGP actually has slightly different behavior when it's configured as the external protocol and when it's configured to carry internal routes. Another thing that I should point out, that even though we call it the internal BGP, even though we call it iBGP, it is actually not designed to replace IGP. It's actually designed to work with IGP to carry these external routes. You cannot just go into your network and say, yeah, I don't actually like OSPF, I'm just going to rip it apart and I'm going to replace it with iBGP. You can try that, good luck. What you should really be looking at is how can your BGP work with your OSPF to make your network most efficient. So this said, there are certain rules that govern the operation of internal and external BGP. Now, let's first take a look at the external BGP. Now, the rules that govern external BGP, and here I'm talking about by default. So all of these things can be changed, and that is the beauty of BGP, is that you can change so many things about it. That's a beauty from the perspective of a network engineer or perspective of a network architect, but from a perspective of a CCIE candidate, the fact that you can change just about anything about BGP is the painful one. Because if you can change just about anything, that means that you can be asked to change just about anything in the lab. But it is what it is. It is a complex protocol. So when we have external BGP, one of the most important prerequisites for external BGP is that external peers are directly connected. Now, this rule exists for various reasons, and I'm just going to give you one of them. So when we have directly connected neighbors, and let's say that this is R1 and this is R2 here, and they are in separate autonomous systems, the expected peering is supposed to be happening between these interfaces because these are the directly connected routes. Now, what is the reason? Why is this expected peering? Because this is the whole assumption. The assumption is that BGP will be the only protocol running between these two autonomous systems. And if BGP is the only protocol running between these autonomous systems, if the routers are not directly connected, we are not going to be able to establish the connection. We might need a helper protocol. Now, in order to sort of ensure direct connectivity, the BGP messages for external peers are by default sent with TTL1. Now, I have often heard from my students when I ask what is the reason for this, is number one reason that I get is that it is security reasons, that we are doing this because we want to have security in place. Now, this is not true. Security is not a reason. Now, the story behind the security assumption here is that if we are expecting packets to arrive with TTL1, the neighbor must be directly connected. Well, let me give you one more example. So let's say that here I have our R1 and R2, and here I have some evil, let me call it evil, some evil device that actually wants to attack this R2. So if R2 is expecting packets to arrive with TTL1, couldn't the evil guy here send the packets here with TTL2? And then when R2 routes these packets here, aren't they going to arrive with TTL1 to R2? The answer is yes. This is how they will arrive. So what sort of security am I getting? None, actually. The actual reason why the packets are sent with TTL1 and why we have this direct connectivity requirement is to avoid a situation where we could possibly have some other path through the network to reach this network here. So if this interface goes down, there is a conceivable scenario that R1 might actually send traffic this way, and then that peering would be useless and pointless because it might go someplace else. So in order to avoid this by default, which is something that you can still implement, something that you can still do, this non-direct peering, in order to avoid this peering from forming by default, there is this requirement that TTL is set to 1 on external sessions. Now, keep in mind that there is a feature which is called TTL security, which does provide security, and it actually ensures that neighbors are directly connected. So if I enable neighbor security between R1 and R2, what I'm going to be doing is I'm going to be sending packets, and this is very surprising sometimes, with the TTL of 255. Now think about it. If I had that previous situation with 3 routers, so I had here R1 and R2, and I had this evil guy, is there a way that this evil guy can send the packet to R2 and still ensure that packet arrives with TTL 255 here? The answer is no. There is no way to do that. So if you enable TTL security feature, what you are going to be doing is you're going to be sending packets with TTL 255, which actually does ensure that the neighbors are directly connected. But keep in mind that for this feature to work, it must be enabled on both sides of this external peering sessions. Another example of BGP peering is, or external BGP peering is, when you might have a situation that you want to have an external peering over non-directly connected interfaces. So let's say that we have R1 here and R2, that they have some interconnection here. Let's say that this is Ethernet 00 and this is Ethernet 00, and we actually want to establish a peering between the loopback interfaces. Now in this case, somehow on R1 we need to have the route to R2's loopback interface, and on R2 here we need to have the route to R1's loopback interface. Now usually if you encounter this ever in the production environment, in the real world, you are simply going to put static routes in place. But in the lab, you are most likely not going to be allowed to use static routes. So in the lab, what you actually need to run here is some sort of a routing protocol, EIGRP or OSPF or RIP. Now, when you do this, you are potentially setting yourself up for a problem. So to illustrate what this problem might be, I'm actually going to show you this in action. So what we are going to have now is I'm going to have a very simple network that consists of just 2 routers to begin with. I'm going to be adding probably more devices to this network. And this is going to be the network between R6 and R9. Now, R6 is going to be in AS600 and R9 is going to be in AS900. On both of these, I'm going to have loopback interfaces, and what I want to do is I want to have peering between these loopback interfaces. So this is a very simple task. Make sure that you have an external peering between R6 and R9 between the loopbacks. Nothing else is provided to you. So we know now that R6 here needs somehow to get the route of R9, and R9 somehow needs to get the route of R6. But I'm not told what I need to do here, so except that this needs to be external BGP session. So what I'm going to do here is I'm going to play smart, and I'm going to set up EIGRP 69 between them and simply advertise these two loopbacks in there. So let me do that now. Going to bring in my text editor, and what I'm going to do next is the template configuration for the BGP peering that I always like to do. Now, there are some things in this configuration that might look a little controversial at first, but I'm going to try to explain them. The first thing that I'm always going to do, so I'm going to say IP BGP community, new format. Now, BGP communities are very similar to route tags, but BGP communities are really just large numbers. So when we are using BGP communities, so I'm just going to quickly have one page here. So it's really just a large number. Now, if you don't use IPBGP new community, IPBGP community new format, what you are going to be seeing is when you do show IPBGP, you are going to be seeing exactly this, just a large number. But when you do IPBGP community new format, what you are going to be seeing is the community in the format that is more common for displaying the communities, which is autonomous system common identifier. So this is sort of this new format of displaying communities. Now, I should point out that this command here, IPBGP community new format, does not actually change the community in any way. It just changes the way community is displayed to us as human operators. To illustrate this point, I'm going to show you something. So here I am on R6, and if I do show IP route connected, this is the output that we are very, very used to seeing. But take a look at this. So I'm going to say terminal IP netmask format, and let's say hex. So if I do show IP route connected, take a look at how the netmask is displayed now. Did I actually change the netmask here? No, I have not. This is the same netmask as I had here. I'm just changing the way the netmask is displayed to me as the human operator. I can also do decimal format. And again, did the netmask change in any way? No, it didn't. The netmask remains the same. It is just shown to me as the human operator in a different format. So I'm just going to put it back to what it is by default. So if I do show IP route connected, that I'm getting this familiar output. This is pretty much the same thing that IPBGP community new format does, except that this command here that I was typing is going to be active only for the duration of my terminal session, and the BGP new format, IPBGP community new format command is actually going to be in the running configuration, so it's going to be applying for all the active sessions on the router. But it doesn't change how the community is actually stored in the BGP tables, and it doesn't change how the community is actually communicated to other routers. Which brings me to other point. Communities are by default not communicated to any routers. So by default, not sent to any peers. And this is yet another thing that I dislike. And if there is one thing that I dislike the most about BGP implementation in iOS, that would be it. That the communities are not sent to neighbors by default. They should be sent, because communities sometimes allow you such a powerful control over the route propagation that you actually need to use, that you're going to be much better off using the communities than not using them. It's a matter of running a single command versus running 15 commands on 15 devices, depending on the size of your network. So my recommendation is, unless you are restricted in the lab from doing that, always, always, always send communities to your peers. So, going back to our configuration here, another thing that I'm going to do, so I'm now configuring R6, so let me go there. So I'm going to say router BGP 600, and this is where usually the most controversial part of my configuration of BGP happens. This is the next thing that I'm going to do. I'm going to type in the command, which is BGP upgrade CLI. BGP, by default, has something that I like to call flat configuration. Now, flat configuration simply means that we have router BGP X, then we are specifying neighbors, and let's say neighbor, whatever the neighbor is, remote AS, then we are saying neighbor, okay, doesn't really work that way, but okay. Neighbor, let's say X. I am going to copy this, though. And let's say that we say password. Let's say that we configure the neighbor here with update source. Let's say that we configure the neighbor here with route map. Let's configure neighbor here with send community. And etc. Now, this is the flat configuration of BGP. Now, when you look at this configuration here, it's not immediately obvious which commands here control the session behavior between these two neighbors and which are the policy commands. I can tell you which ones are which. These commands here are the session commands, and these commands here are the policy commands. Now, session commands are the commands that control the behavior of the TCP session. So here we see that it is going to be in that remote AS. So this is something that we are going to check when we receive the open packet from the neighbor. The password controls what is going to be the password on the session, the update source, where are we going to send the update source from. But the policy commands, they modify the behavior of the routes, either sent routes or received routes. So we can say that basically BGP configuration commands are divided into two categories. We either have, or I should say BGP configuration commands. They are divided into either the session commands or the policy commands. Now, session commands can be either global, that means they apply to all address families, and here I mean IPv4, IPv6, VPN-v4, IPv4 multicast, and so on, or they can be per address family, but policy commands, so let me write this a little bit more clear. The policy commands are always per address family. But if I take a look at the flat configuration of BGP, it is not immediately obvious that this here applies only to IPv4 address family, which is okay. This is the reason why I am actually always going to implement my BGP configuration in the new format that actually forces me to use the address families. I should mention here that this is again just a cosmetic change. The behavior of BGP does not change in any way after I do this. Now, when I enter BGP update CLI, upgrade CLI, I'm going to be asked, are you sure you want to upgrade? There is no going back. And this is why I'm typing that yes there, because I'm telling the router, yeah, I know what I'm doing. I want to upgrade the CLI. Now, I should point out that there is another way to upgrade the CLI, and it will be this. Done. After you have done this, the upgrade of CLI has happened, and the command BGP upgrade CLI is no longer available. But the point is that this command on top there, so let me put this in a whiteboard so that I can explain it there a little bit better. So this command, this configuration here, this is an explicit upgrade. And this one here is an implicit upgrade. So here I'm explicitly requiring the router to upgrade, and here the router will simply do it for me. In my experience, the implicit upgrade sometimes provides, sometimes makes an incomplete translation. So what you end up having in the running config is not necessarily what you wanted to have configured. This is why I suggest, if you need to use multiple address families, always use this. And even if you don't want to use multiple address families, always upgrade your CLI. Because this new format of configuring BGP is where iOS is moving these days, is where iOS XR is moving these days, and is where definitely Nexus is moving these days. So my recommendation is that you always upgrade your CLI, and that you always use this explicit upgrade of CLI and not implicit one. So the next thing that I'm going to do here is I'm going to specify my neighbors. So I'm configuring R6, so a neighbor will be 192.168.0.9, remote AS 900. So let me just correct this typo here, and while I'm at it, copy this. So here I'm now specifying just the session commands. I'm going to have the update source of loopback 0, and because it's an eBGP session that is not between directly connected neighbors, I'm going to be using eBGP multi-hop, and this is pretty much it. I don't really need any other configurations. Now I'm moving into the address family configuration, so address family IPv4, and if you want to be really complete, you can say unicast here, and then I'm going to say neighbor activate. Now technically speaking, activation is automatic for IPv4, just like it was before, just like it was in the flat configuration. This is what I meant by this does not change the behavior in any way. So this here is a completely optional command, but I'm going to type it out anyways. The next thing that I'm going to do here is I'm always going to say send community. Now, here I have three possible options. One is to simply press enter. The other one is to say standard. And the other one is to say both. Now, if I just press enter, that is really the equivalent of typing the standard. If I type both, no, actually, apologize, there is one more option. So let me just send this. So I have extended and both. So these are the options that I have available. So if I just press enter here, it is the equivalent of me saying that I want to send standard communities. Now, extended communities for IPv4 address family is something that you are almost never going to see unless you are using the feature that is called DMZ link bandwidth, which uses BGP cost community, which I find very, very unlikely. And both here simply means that you will be sending standard and extended communities. Now, I usually, for IPv4 peerings, just press enter here, but if you want to be on a really, really safe and paranoid side, you can say both. In the examples that I will be doing today, I will not be needing any extended community, so I'm just going to say send community. So this is the configuration on R6 that I'm going to do. And I'm going to keep this configuration because, as you will see, it is going to come back very, very often. And when you go into the BGP session, it makes, when you go into the BGP section of your lab, it makes very, very good sense. It makes so much sense to actually keep these templates, because when you're configuring multiple routers for BGP sessions, you'll be surprised how much copy paste you can actually do. So if I go to R6 here, I can see that this is where I was being asked, am I sure that I want to actually upgrade this configuration to the new address family syntax of BGP commands? I'm answering yes, and then we are taking it from there. So on R9, the configuration is going to be pretty much the same, except that this changes to 900. This here changes to 6. I'm cheating a little bit there, but you'll forgive me. So I'm going to go to R9 now, going to paste this configuration in, and my neighbors are not going to come up. Why are my neighbors not going to come up? Well, if I do show IP BGP summary, I'm going to see that the neighbor is active. Do I actually have the route to this neighbor? I don't, because remember, what is it that I actually have to do here? What I need to do here is I need to build EIGRP so that the loopbacks are reachable. This is something that I have not yet done. So let's do that next. Very, very simple configuration of EIGRP. Let me bring in my text editor here. Going to open another window. Going to keep this configuration safe because I will be needing it a little bit later on. And in this one here, I'm just going to say configure terminal, router EIGRP 69, no auto summary, and network 192.168.69.0. This is where I need it, and let's configure it on 0, 0, which will enable it on the loopbacks. Because remember, if I don't specify the wildcard masks for EIGRP, the network statement is classful. So this will cover the network between R6 and R9, and this will cover both loopbacks in my case. So on R6, on R9, and now when I enter this command, I can see that EIGRP now has the adjacency, and if I do show IP BGP summary now, I will see that BGP, and here just in the meantime, BGP came up, and I can see here that status is no longer active as it was here. I can see that the status now says 0. Now you can see here it says state or prefixes received. So now this is telling me that I have 0 prefixes that I have actually received from BGP, which is good because I haven't advertised any prefixes. So this would be a very basic configuration of this external BGP. Let's go with another example. So I'm going to add something to my network here, and I'm going to add router R2. So let me just bring this here. So I'm going to do a little bit more magic here. So this is what I'm going to add now. I want to add R2 to AS600. Now this R2 is going to be running OSPF in area 0 with R6. And there will be 1 or 2 more routers, so I'm just going to put this here. And what I want to do is I want a very, very simple peering between R2 and R6 that is going to be internal peering. So let's use red there. Between the loopback, so I want to have iBGP peering between R2 and R6 between the loopback interfaces. Now, these interfaces here are already configured for OSPF, and all I have to do on R6 is actually do no shutdown, and OSPF will come up here and the loopbacks will be advertised. So let me go back to my terminal, and I'm actually going to bring in R2 to the mix. Let me put it all the way to the left here so that it resembles what we have on the diagram. And on R6, I'm going to say interface serial 010 602. I'm just going to say no shutdown. So as I said, this is all pre-configured now, and I can see that I already have OSPF that came up, and if I do show IP route OSPF, there we go. If I do show IP route OSPF, I should have the loopback of R6 available. So if I do ping between R2 and R6, this works on R6. If I can ping R2, I know that my OSPF works. So let's do show IP route OSPF here, and I have the loopback of R2. So all I want to do now is bring the BGP between R6 and R2 up and running. Well, this is where this configuration is now going to come in very, very handy. Because take a look. What I need to change here is this. I don't need eBGP multi-hop. Everything else is pretty much the same. So this now can go to R2. There we go. And what I need to do on R6 is basically change this to 2 and paste it in. Now mind you, I'm going to get these couple of error messages here. Do I care about them? Not one bit. So now I have the peering between R2 and R6. Now this peering here is an internal peering. Now for internal BGP peering, there is no requirement for direct connectivity. The routers can be actually several hops apart. They can be very, very distant from each other, and that's perfectly fine. We don't have to have direct connectivity to have iBGP peering up and running. So this is exactly what we have right now. So there is this peering between R2 and R6, and again, we are receiving 0 prefixes. So let's go back to our whiteboard and let's add one task to the mix here. So what I want to do is I want to have reachability between R2's loopback and R9's loopback. Here are the restrictions. Ping R2, R9, loopback interfaces, no redistribution, no new interfaces, yeah, that's pretty much it. And yes, let's add no new protocols. So I cannot add any new routing protocols, I cannot create any new interfaces, and no redistribution is allowed. And I have to ping between R2 and R9. Well, I'm thinking here, this is very simple. R2 is running iBGP with R6, and R9 is running iBGP with R6. So if I advertise the loopback of R9 into BGP on R9, it will arrive to R6 and then be sent to R2. Also the other way around. Let's first start with R2's loopback. So I'm going to go to R2 here, and I'm going to go into router BGP 600, and I'm going to say address family IPv4. Remember, this is a policy command, so the policy commands need to go into address families. Why is it policy command? Because now I want to cause the route to actually be advertised in BGP. I'm not allowed to do any redistribution, but I can use the network statement. So network statement in BGP is very different than the network statement for IGPs. For BGP, the network statement says, if you have a network in the routing table that matches this statement exactly, advertise it into BGP or inject this route into BGP. So what I'm going to do here is 192.168.0.2 mask. So this is the network that I actually have in my routing table. So if I do show IP route, I will see that I actually have this /32 route. It's directly connected So now I'm telling my router, advertise this into BGP. And now I can see that this route is being advertised into BGP. Now, a couple of things that I wanted to point out here. When you are injecting the route on the local router, the next hop for the route will always be all zeros. This doesn't mean that this route is following some default route. This means that this is a locally injected route. Locally injected or locally generated routes will always have a weight of 32,768 by default. All this can be changed by using route maps. Also, the metric, the multi-exit discriminator, will be 0 by default, and the local preference will be 100 by default. It's the default, so for internal routes, you're not for locally generated routes, you're not going to see the local preference if it has the default value. So this route is now injected into BGP. We should now check if this route is actually being advertised anywhere. I can do that if I do show IP BGP 192.168.0.2. If I run this command, I will see that this route is being advertised to update group number 1. Now, update groups are automatic optimization of route advertisements to different neighbors. If the neighbors are sharing the exact same set of policies configured on them, again, that word policy, if we have the neighbors that are sharing the exact same set of policies, they're going to be automatically put in the same update group. So in this case, we have only one neighbor and we have only one update group. So if we do show IP BGP update group, we are going to see that there is this update group that has only one member, which is 192.168.0.6. So from what we can see, this route is actually being advertised to this neighbor. There is one more thing that we can do, which is show IP BGP neighbor 192.168.0.6 advertised routes, and here we are going to get the list of routes that are actually being advertised to our neighbor. So from R2's perspective, it looks like we are indeed advertising this route to R6. So let's take a look at R6. If I do show IP BGP summary on R6, I now see that from R2, I am actually receiving one route. Let's see which route that is. So if I do show IP BGP, now I see the route from R2. The next hop is the loopback of R2. I can see that the metric is 0, the local preference is 100, the weight is 0 now, and the path is empty. This I is something else, I will talk about it later on. But more interesting is this little r, which says rib failure. Now, failure is bad, except in this case, it's actually not that bad. Rib failure here is not the problem. Rib failure here simply tells us that as far as this router is concerned, this is the best route, this is a valid BGP route, but it is not the one that is installed in the routing table. Why? Because if we take a look at the routing table, there is a better route from OSPF. Why is this route installed? Because it has distance of 110. This route here is an internal route, so this little I here tells us that this is an internal route. Internal routes in BGP will have the admin distance of 200, which means that based on the admin distance, this route loses out to this route, but it is considered to be the best route, and this is still a valid route, which means that this route, so if I do show IP BGP 192.168.0.2, this route is still going to be advertised to someone. So if I do show IP BGP update group, I see that on R6 I actually have two update groups. That's also perfectly normal. And one update group here consists of 192.168.0.9, and this one consists of 192.168.0.2. Why do I have two update groups? Because I have two neighbors that have different sets of policies. Why do they have different sets of policies? Because one is internal, the other one is external. There is difference in policy there. So this is the update group number 1, which consists of 192.168.0.9. So if I take a look at this, R6 tells me that it is actually advertising this one route to R9. So if I go to R9, if I do show IP BGP neighbor 192.168.0.6 routes, I will see the routes that I'm receiving after my local filters have been applied which there are none. And here I can see that I am actually receiving one route. So if I do show IPBGP summary, I can confirm that. And if I do show IPBGP, I can actually see that this route is received. A thing to note here, that this is now considered to be a valid route and is considered to be the best route. Why? Because here between R6 and R9, there is no other protocol that actually communicates this one route. So on R9, if I do show IP route BGP, or if I just do show IP route, I will actually see that 192.168.0.2 is now present in R9's routing table. So this is how the route propagated from R2 to R9. Now, let's add the network. So here, router BGP 900, address family IPv4. I'm going to say network 192.168.0.9 mask 255. So now I'm adding the loopback of R9 to the mix. If I go to R6 and if I do show IPBGP summary, I will see that from R9 I'm now receiving that one loopback. If I go to R2, if I do show IPBGP summary, I see now that from R6 I'm receiving one route. If I do show IPBGP, this is the route that I'm receiving from R6. Take a look at this. It says here that this is a valid route, but it's not the best route. Why is it not the best route? Well, we can't probably tell directly. So if we take a look at this route, we are going to see here that it says it's inaccessible. It's inaccessible because the next hop for the route is not in the routing table. So when R6 actually advertises the route to R2, it is going to keep the next hop of the route that was originally available on R6. That means that we might need to have this loop back here in the routing table on R2 to actually use this loop back. That's kind of weird. So what I'm going to do here on this session in this direction on R6, I'm going to add a policy command which is next hop self, which is going to tell R6 when you're advertising the routes to R2, change the next hop parameter, whatever it was, change next hop attribute, whatever it was, change it to your update source. So if I go back to my terminal and if I go to R6, router BGP 600, address family IPv4, so I'm going to say neighbor this, next hop self, and let's just speed it up. I'm just going to clear the sessions. Okay, so now if I do show IPBGP summary, should be seeing two routes. If I go to R2, same command, show IPBGP, now I can see that the next hop for this route is 192.168.0.6, and this is the metric to reach it. So now on R2, if I do show IP route, I'm actually going to see that I have the route to R9. If I go to R9, if I do show IP route, I will see that I have the route for R6. If I go to R2, and if I try to ping this route, it is going to fail miserably. Now, this is the problem that I wanted to show you. I have set you up, or set us up in this network about 15 minutes ago. There is a huge problem in our network. You may or may not see it at this point, but the problem is that everything on these devices points that everything is fine. If I do show IPBGP summary, this looks like it's okay. If I do show IP route, everything looks like it's okay. On R6, show IP route, everything appears to be okay. On R2, show IP route, everything appears to be okay. From R2, I can ping R6, that looks okay. From R6, I can ping R2, but from R6, I cannot ping R9. Why can I not ping R9? Well, I can tell you right now, but I'm actually trying to buy myself a little bit of time. And actually, the amount of time that I'm trying to buy for myself right now is about 60 more seconds. So I'm just going to be silent here for about 55 seconds at this point, and I want to show you something. So I'm just going to sit here absolutely silent. Which is very hard for me to do, I have to admit, because I'm used to talking. Patience is a virtue, just not one of mine. And this is exactly what I wanted to show you. So at one point here, we see that we are receiving the notification and that this neighborship between R6 and R9 is going down because the hold down timer expired. Hold down timer in BGP is 180 seconds, 3 minutes. If in those 3 minutes we are not getting any TCP keep alives from the other side, the BGP session will be going down. So when this session went down, it immediately came up. Now, you can take my word for it that in about 1 minute, or actually 2 minutes and 20 seconds, this is going to happen again. So this is now having a problem again, and I can prove you that. So if I try to ping R9, I cannot ping it. That means that TCP keep alives are not going across. But if I do clear IPBGP star, actually I can ping R9. But now when the BGP comes up, I can no longer ping it. Well, of course, every time I want to show you something doesn't work. So let's give it just 1 second here. It is going to take just a little while for this to, there we go. Now we have a problem. So what is happening now is I cannot ping it. And if I try to ping it now, it won't work. That was just a tiny little fluke there that we could actually ping it. BGP was doing something in the background. What is happening now, if I do show IP route, take a look at this route. This is the route for R9. Take a look at the admin distance. The admin distance is 20, external BGP. So the moment we actually advertised the route here on R9, the moment we've done this, we have basically created the problem for ourselves. Because now, when R9 advertises the route to R6, this is going to be a perfectly valid BGP route. It's going to get across. And what is going to be the next hop of this route? It's going to be itself. So if I do show IP route 192.168.0.9, it tells me that it's reachable through itself, which happens to be reachable through this route, which has this next hop. So we basically have a recursive routing problem. Now, when I clear the BGP, when BGP disappears, so let me clear it. If I do show IP route, I will see that EIGRP route is now the best. But take a look, EIGRP route has the admin distance of 90. But now, okay, BGP is again slower than I wanted it to be. Okay, it's not yet up, now it's up. So if I do show IP route, now I see that BGP route has taken over. So when the BGP route takes over, we can no longer have reachability between R6 and R9. So now our hold down timer goes down. What is happening in the background is when this goes down, it's the equivalent of me clearing the session. EIGRP route comes back into the routing table, the BGP peering session reestablishes, the route gets re-advertised, and we have the problem again. Repeat ad infinitum. Now, the problem here is this admin distance. So how do we fix this problem? How do we solve this issue? Well, there are multiple solutions. One is, of course, I can modify the admin distance of EIGRP to be 19 or less, or I can modify the admin distance of external BGP to be 91 or above. Or I can use a feature that is called backdoor link command. Now, backdoor link command is something that I'm going to configure on the side that experiences the problem. Now, in this case, R9 doesn't actually have a problem, because on R9, I actually have a correct EIGRP route for R6. Because remember, we are not advertising R6's loopback in BGP, only R9's. So on R6 side, what I am going to do is I'm going to go to router BGP 600. I'm going to say address family IPv4. Again, this is a policy command. And I'm going to enter the command. I'm going to enter the network statement for the command, for the network that is causing me problems. Now, if I press enter here, what's going to happen is BGP is going to advertise this route into BGP, but this is not what I want. What I want to do here is I want to declare this route as the backdoor route. What this does internally now on the BGP process is it tells R6 that if you receive this route from an external peer, instead of giving it the admin distance 20, give it the same admin distance you would give to locally generated routes. Now, locally generated routes in BGP in iOS have the same admin distance as internal routes, which means that effectively I'm telling my router, if you receive 192.168.0.9/32, instead of giving it admin distance 20, give it admin distance 200. So now, if I do show IP route, what I'm going to have in the routing table is R9's route, which is now EIGRP. So if I do ping from R6 to R9, that works. But also, if I do ping from R2 to R9, this actually works. Actually, this was to R6. Let's ping R9. The ping to R9 also worked. From R9, I'm going to ping R2. So this was an example of the danger that you can have when you have an external peering between interfaces that are not directly connected, especially in combination with the routing protocol that is used to carry these interfaces. Now, in real life, this is a very unlikely scenario, because in real life, you would just put the static routes in place and you would be fine. But in the lab, you are most likely going to be asked to use dynamic routing protocol for this purpose. And it doesn't matter which one you use, they're all better than the external BGP routes.